Hi, ladies and gents. Let's jump into Excel and take a look at how we do ANOVA tests using Excel. I've got a questionnaire here. This is an example of a bad questionnaire. And I go through this in a set of videos called data cleaning. There's 5 of them there. And so you can take a look at those. You'll find those in the lab video section. But this is taking a look then at a number of different measures for Business Admin 111 students. And I've also added a few questions at the bottom here then for different types of questions. And if you take a look at that data cleaning set of videos, they'll talk about how to clean up the data. So what I've done is I've actually cleaned that up. So this is a copy of the clean data here. And so we've got a column for every question. Some of them are check all that apply questions and ranking questions, and so there's more than one column for those questions. And then each row represents a respondent. And take a look then at those videos on data cleaning in terms of the setup and how we fix up all the different errors here. But what I'd like to do here then is to take a look at how we use ANOVA to look at the relationship between two variables. Let's say the section number and the number of siblings. See if there's a relationship there. So the section number is the section of Business Admin 111 that they're in. And then the siblings is, of course, the number of brothers and sisters that they have. So that is a nominal variable section. And then siblings is an interval variable. So nominal versus interval, that looks like a good candidate for ANOVA. All right, let's make a copy of this. So I'm going to go down to the bottom here and right-click and choose here, move to copy. I'm going to choose create a copy. And so now what I've got is a set of data here, which is identical to the clean data tab, but I'm not going to touch the clean data tab. I'm going to just use this one right here. Now, let me actually just increase the zoom a little bit here, and I'm going to get rid of all of the columns here except for the section number and the siblings. So let's delete those. And I always keep the respondent number. And that's because we tend to have some blanks all over the place. You can see there's lots of holes in the data where people didn't answer certain things, but everybody has a respondent number. What I do is I highlight a particular row here and I color it so that when I sort the data, it's important that these columns all sort together. So let's first of all just clean up the data a little bit in terms of whether there's any blank values here. Because when we're taking a look at the relationship between two variables, then the respondent has to answer both questions. So we have to have data for both of the columns. So I'm going to click on the section column, and I'm going to go up here to the sort A to Z. You can also find that in the data menu here, A to Z. And so I do that, and what happens then is I come down here, and I've got all the A's, the B's, the E's. This is actually real data. There was a section A, a section B, and a section E. But respondent number 22 here actually didn't put down their section number. So we're just going to get rid of that particular row there. Now let's do the same with the number of siblings. So I'm going to sort according to the number of siblings. And it looks like up at the very top here, we've got 0 siblings, which is fine. And then down at the very bottom here, we've got respondent number 34 did not put down an answer, so we're going to get rid of that row there. I'll get rid of this blue one as well. And you'll notice here that the color cells stayed together. So these sorted all together, which is nice. In fact, that's necessary. All right, the next thing that we do is we go to the nominal variable. So the nominal variable is the section. and then the interval variable is the number of siblings. So we click anywhere in the section variable, which is the nominal variable, and then we do a sort. So data sort, and we'll just scroll up here to make sure that those guys stayed together. Yep, the orange cells stayed together, so the siblings sorted along with the section. And now what we're going to do is we're going to unstack the data. So there's 3 different sections, A, B, and E. And then what I'm going to do is go and grab the sibling numbers for the A's. So for section A, I grab the siblings. I'm going to copy that, and I'm going to paste it over here. And then I'm going to come down here, and I'm going to grab the number of siblings that correspond to the B's. Like that. So I'm going to copy, or I could cut that, of course. And make sure that you scroll all the way to the top here, and then paste right underneath the B. And then we're going to go down here to the E's. And I'm going to grab those people. Copy, go up to the E's, and paste. Good. So now you can see that we've got 3 different columns here. There are 3 different treatments, and they are unstacked, and they have different numbers in each case. So I want to show you actually 2 tools that you can use to do an ANOVA. The first one is that Excel has a built-in ANOVA feature. And so if you go to the Data tab, which I've already got open here, at the far right, you should see something called Data Analysis. Now, if you don't see that, then you're going to have to add that in. And so it's called an add-in. And I'm using a Macintosh, a Mac, so I go to Tools, Excel Add-ins, and I just make sure that I've got the Analysis Toolpak selected, so checked, and then I press OK. So I've already done that. If you're using a PC, you'll find that it's going to be under the File menu, and then you'll go down here, and you'll see that it'll say Options, and you'll choose Options and then Add-ins. So we don't have that in a Mac, but you can find that there. If you have trouble with that, you can go to the Supplementary Files folder, and you can find that there's a little file there that talks about how to add in the Analysis Toolpak. So once we've got that, then we're going to click on Data, and then over to the far right, Data Analysis. And you've seen this before. I mean, this is where we had descriptive stats, for instance, and we've done z-tests and t-tests and so on. But we're going to go to the very top where we've got ANOVA single factor. And we're going to press OK. The input range is really easy. Once the data are unstacked, so that means that these are all number of siblings under each of the treatments, the different categories of the nominal variable, then all we do then is we highlight the whole bunch, including the titles at the top, so the name of the treatments, all the way down to the length of the longest treatment. So right there. It's already grouped by columns. We're going to tell it that we have labels, and then we can choose an alpha here. It defaults to 5%. We can choose an output range, and I'm going to come up here and then find a cell and then press OK. So before I press OK, you might want to stop the video and just take a look at that and just make sure that you understand how all of that is set up. All right, I'm going to assume that you've done that. So I'm going to press OK. And this is what we end up with. Let me actually just make this a little bit bigger here because it's a little hard to see with 11 point font like that. So this is what we've got here. And of course you can change these then to a couple of decimal places like that. Under the Home tab, you can decrease the decimal places. I usually take it to about 3 decimal places. And then you can do that with these guys too. Okay. So there we go. And in our particular case, this is interesting because what we've got is that there is a relationship between them. So if you take a look at your p-value here is quite small. It's 0.004, which is certainly less than 0.05 or any alpha that you would have. It's even less than a 1% level of significance. And so that would indicate that the means are significantly different from each other. Alternatively, here's the f star value, the computed f value, and we would compare that then to the critical f value. It's always an upper tail test, so we would say 5.968 is greater than 3.115, so we're going to reject HO. Now, I haven't written out the HO and the HA, but the HO is that the means of the populations from which these values come from are equal against the alternative that they're not equal. So in our particular case, then, they're not equal, and you can see here that section A has, it looks like a lot more siblings than section B and E in terms of the averages. And if you take a look at the data down here, you'll see that there are some students here that actually have a large number of siblings here. So that's what's causing that. Now that's useful. The problem is that we would then need to do a Fisher's comparison where we would take a look and see, well, which ones are significantly different from each other? Are they all significantly different from each other? Or in this case, it looks like A is significantly higher than B and E, but we don't really know whether B and E are significantly different. The other thing, and even more importantly here, is that ANOVA depends on certain conditions. So the condition here of normality, that is that the population from which A comes from, the siblings, the distribution of siblings are normally distributed. The same with B. These have to be normally distributed. The same with E. They're normally distributed. And then if normality holds, then we do something called a test of homogeneity of variance. That is, the variance have to be equal for each of the treatments. So that can be an onerous process here, but I want to introduce you to a template that I've created here. And so you'll find it in the supplementary files folder, and it's called the ANOVA Template. Now I've made a copy of it, but it's called ANOVA Template, and it's an Excel file. And all you do here then is you go back here, take your unstacked data. So you still have to unstack it, put it into the 3 different treatments. I'm going to copy that. And then I'm going to open up that file. And I'm going to come down here. Let me just make this a little smaller to begin with, and then we'll take a look at it. And I'm going to click in this orange cell right here next to where it says treatments. Now, incidentally, in this and the next several tabs here, the only place that you can actually change the values or paste values are in the orange and yellow cells. So when you take a look at the next pages, actually, you can't even change any of these values in these next few pages here. So what we do then is we click where it says treatments, and you can just simply do a straight paste. I usually do a paste special, so click on the down arrow here next to paste and choose just paste values, and that just keeps the nice colors here. So what we end up with then, let me actually increase my zoom. So I end up with actually exactly the same results as I had before. We have an F star value of 5.97, and that's what we ended up with right here, 5.97. The p-value is 0.004, and the critical value is 3.115. And so over here, it's there's the 0.4%, 0.004, and here's the critical value, 3.12 when you round it to 2 decimal places. And if you check the numbers in the ANOVA table, you see the SS, B, and W, and T values, and so on are all exactly the same. So what you can do here is you can copy this like this and go right down and grab the names of the treatments here. But don't take any of the yellow cells, because you can actually have, in bigger data sets, you can have actually dozens and dozens of rows here, and you don't want to copy that. So just these cells right here. And so I'm just going to do Control-C here, and I'm going to move over to a blank page. Let me actually just open up a new document here, right there. And I can just paste this. And there's my output. Let me just change this zoom here a little bit so you can see that. Now, what I would do here is go in here and change these to the specific treatments that we have. So we've got section A, section B, and then section E. And you can just kind of clean that up a little bit like that. You can actually make those subscripts there if you want. And that's just a little cleaner here. Now, in our particular case, we reject HO, and that means that there is a significant difference between at least one of these means is different from the others. And so here we've got the means, the sample means, and you can see what they are. You can see the variances, you can see the ends, and so on, like that. But I'm going to go back to the template now, and I'm going to grab this part, because these are the Fisher's multiple comparisons. And I can just grab those guys. I'm going to copy that and move over. And just down here, I'm going to paste that. Now, the multiple comparisons is useful then to show you which one's actually different. So remember what the Fisher's multiple comparisons are, is they show you the difference of means between the two treatments, A and B in this case. So it's going to be always your column total minus your row total. So A minus B. Now it's the population mean of A, the mu of A, minus the mu of B. And then we build a confidence interval around that, a margin of error around that to build a confidence interval. So what we're saying is that A is anywhere from 0.3 to 2.25 higher than B. So that's the average number of siblings, anywhere from a third of a sibling to just over 2 siblings. The important thing to note here is that both of these have positive signs. So when the signs are both positive or both negative, right? If A was less than B, significantly less than B, then you'd end up with negative signs. If the signs are both the same, it means that there's a significant difference between them. So similarly with A and E, what we're saying with A and E here then is that A is anywhere from 0.7 to 2.9 siblings more on average than E. So this number here, of course, is the sample mean up here, and the sample mean here for E, and we build a margin of error around that. But this is interesting in terms of B and E. What we have here is a negative lower bound and a positive upper bound. So when you have a negative lower bound and a positive upper bound, that means that interval looking at the difference of the population means contains 0. And that means that they are not significantly different from each other. So we're saying that although 1.76 is higher than 1.24 in terms of sample means, they're not significantly different from each other. So that's how we would do this problem here. We would conclude that there is a significant difference and that A has significantly higher number of average number of siblings than section B or section E. So that's how we use then this ANOVA template. Oh, we're not done with the ANOVA template yet. I want to get back here because remember, a big part of ANOVA here is to check to see whether the conditions hold. So what we do in this case then is we go down here and we say, well, normality is an important condition here. So if we go here to normality, there's a normality tab, then we click on that. And we got some problems here. So this is the Anderson-Darling test for normality, and it's actually 3 separate tests here. So it's a test for A, a test for B, and a test for E. And in each case, the null hypothesis is that the data are normally distributed. And so if you reject HO, then it means that you've got a violation of normality. Now, you only need to look at a treatment if the n is less than 30. So if the n is 30, which it is in this case here, you don't have to worry about this reject HO. So you don't worry about B because the central limit theorem kicks in when n is greater than 30. But for n less than 30, in this case we've got, for A we've only got 25, we look down here and it says reject HO. And similarly for C, we've got only 21 and we look down here and we reject HO. The way this works is that if all of them are greater than 30, then you're fine, right? But for any treatment which is less than 30, if you end up rejecting HO for any of them, then we've got a problem with normality. Normality does not hold. It means we go to a Kruskal-Wallis test. So even if this one, for instance, let's say section E was do not reject HO, we'd still have a problem with this one right here, reject HO. So just one of those, reject HO, for an n less than 30 causes you to say normality does not hold, so we go to the Kruskal-Wallis test. If normality passes for all 3 treatments here, you go to the homogeneity of variances. And the homogeneity of variances page is where you've got a Bartlett's test. This is testing the 3rd condition, that you have to have equal variances, which is the null hypothesis here. So rejecting HO is a problem. And what you want it to say is do not reject HO. A last point, though, is that you don't even look at this page if normality fails. So normality failed here, so we don't even look at this homogeneity of variances. In fact, the Bartlett's test only works if normality passes. So in our particular case, then, we look here and we say, we got a problem actually with both A and C, or E, this is, I guess. And so normality fails. So right away we go to the Kruskal-Wallis test. And the Kruskal-Wallis test then is where we change the numbers into ranks, and the computer does that automatically for you. And so it actually becomes a test of medians. And so we would look here and we would come up with reject HO. Now what you do is you look at the adjusted values here, and when we did this in class, if you did this by hand, you would actually get this particular value here, but there is an adjustment here. It's just an extra formula that you use, and we're not going to do that by hand in class, but I'd always like you to use the adjusted values. So in this particular case then, this still tells us then that you reject HO, very low p-value here, And we take a look then at where the differences lie. You want to look at the medians. And the medians here then show you then, now remember this is the median number of siblings. So this is telling us then that it looks like section A here then has a higher median for the number of siblings, and then that's followed by B, and that's followed by E. One thing we can't really tell here is whether 2 and 1.5 are significantly different from each other, and whether 1.5 and 1 are. I suppose what we could say is that the highest and the lowest have to be significantly different if we reject HO. So we could conclude that A is significantly higher than E in terms of the number of siblings. Now, typically what I do in this case here is that I look at this and I would say we end up with the same results as in ANOVA, and so we can still report the ANOVA but include the output from the Kruskal-Wallis and say that the Kruskal-Wallis is more reliable because the normality conditions fail. But because they agree with ANOVA, then we can summarize it using the ANOVA. So I would go over here to normality, and I would copy this right here. And I would move over here. And I would put it down here. And it's not good to actually split this over a table, so you'd probably want to move this down to the next table. And then I would go over to the Kruskal-Wallis, and in the Kruskal-Wallis I would take this like that, and again just down to the treatments themselves here, and I would copy that. And move down here. And with your Kruskal-Wallis, you should go in here and you should change these to A and B and E, right? So that is what you want to do there. Right. So when you're writing this particular one up here, then what you say here is that the ANOVA results give us this. Up here, we reject HO. However, the Anderson-Darling test for normality actually fails, and you can highlight these parts here, right, and color them. And so that means then that we should be looking at the Kruskal-Wallis test, and so we come down to the Kruskal-Wallis test, and here we end up rejecting HO. And so that supports then our, that's actually the same results that we got from before. By the way, you might have to adjust these columns a little bit here. And that's an easy thing to do once you find where they are. Once you find where they are. It's right there. Okay, there we go. And the same with this adjust for ties. I'm not going to do that. But that's how you would do that. And so we are rejecting HO. We can see the differences here. So you can explain the differences in terms of the medians and that they agree with what we've got up here in terms of the differences of the means. So it looks like A is higher than B and E, according to this. What we really can't tell is, well, we can tell here that A is higher than E, the smallest one. We can't really tell if it's higher than B. ANOVA tells us that right here. But remember, we can't trust ANOVA. So the Kruskal-Wallis, we can say at least the highest is higher than the lowest there. So that's how we would use this ANOVA table, this ANOVA template here, to do an ANOVA problem and test the conditions and use Kruskal-Wallis if you need to. One thing I want you to notice is that in the output, I did not include the Bartlett's test because we don't even get to the Bartlett's test. You would only include the Bartlett's test output if normality passed. Then you'd have to stick it in and see if it passes. If it fails, then of course you would go on to use the Kruskal-Wallis test. Okay, that is what I wanted to show you today, and so that is where I'm going to end this particular video. Thanks for watching.